So hopefully you've watched the first video. Hopefully you've watched both videos, but I'm going to walk through some of this just briefly, just because I don't have the time. Yeah, I definitely don't have the time. Valence electrons. It's really awkward in this environment, as I said in the video. This periodic table, I have this placemat, which is awesome, that I was missing at my mom's, has the two different ways of labeling, with the new way where they just count across 1 through 18. They've actually came out with a new periodic table. I think it was over the Christmas holidays or beginning of January. And actually I haven't looked at it because there's been so many different periodic tables. The periodic table turned like 150, or it is next month or something like that. But when we're in the classroom, I don't have this awkwardness because we all have the same periodic table. But I do recommend, if yours just has the numbering of 1 through 18, that you may want to put the A group numbers there. It can be helpful, but you don't have to. But the A group numbers was a way that helps us to see valence electrons. The B's is a whole different thing. But the idea of valence electrons, we get into electron orbitals the last 2 weeks of the term, but valence electrons are the outermost. And I just realized that saying this, I don't know what I said in the video. Because when I was at my mom's, I didn't have the board I had was mine from when I was a child, and it turns out it's quite small because I was much smaller. But the outermost means that these are the reactive electrons. And they are the ones that matter. And so they are their A group number. And so it can be helpful to have these numbers. The octet rule, I will tell you this. In Chem 222, we ignore the octet rule as much as we obey it. The octet rule is that they all want to be like a noble gas. So a noble gas, in honor of our Buddha question, is nirvana. And so that makes it a happy, content, unreactive. So then they become unreactive, meaning they're stable. So in nature, everything's already reacted. So when they're in the rock form, they've reacted. Sodium is as sodium ion. It's not that reactive. For those of you who are at Damon's, or several people did the alkali metals, they're highly reactive because when we made them into the metal form, because they don't want to be like that. They want to gain or lose or share electrons. So the octet rule is that they want 8 valence electrons, like the noble gases. That rule, turns out, is a rule. It's not a law. There's no real laws out there, actually. But it's true for carbon, nitrogen, oxygen. And we are carbon-based beings. And so it's really important to a biochemist like myself. The rule gets broken a lot. This term, we're going to pretty much go with it. All right. Cations are positive. So I talked about that. That's why you're going to see me dressed like a cat. And I do offer that as an extra credit if you dress up like a cat. My other class last term, a lot of them took me up on it. Or if you want, you can dress up as an onion. So I had a student who's from England, and he actually, everybody else in the world apparently says it like they do, which is cation and anion. So we are actually the ones who say it different. But we say cation and anion. Cations are the metals. Just, I went through this in the video, but the quick short thing. Oh, that's why I did put it down here. So there's the periodic table with the A group numbers, and the nonmetals are going to form the anions. So that means they gain electrons. So over here, and that's where that nice black line, on this side of the black line, they gain electrons, and over here, the metals lose electrons to become like a noble gas. Now with this is all talking about in nature. There are exceptions, especially in man-made processes. that they've often been able to tweak some things. And also the ones that are the metalloids, sometimes they can be switch hitters, but we're going to try and go with a purist thing and say, okay, the ones above this line are going to form anions, and the ones below this line are going to form cations. There's one other big exception, and I talk about that, and we'll talk about it today, and that is hydrogen. And so hydrogen is, again, you can Google, there's so many different periodic tables that they're trying to come up with. Part of it is to deal with this anomaly of hydrogen. Hydrogen is a nonmetal because it is a gas. But hydrogen readily actually forms a positive ion. And so that's why we show it in the periodic table with the positive ions. It's not actually truly a positive ion. And so it's going to be in a special category all of its own, which is as a proton. And that's when we talk about acids, which we'll get to in about an hour. This is so much easier when I have the board, like 5 boards behind me, and all of you that I can see your faces. All right. Predicting charges. So again, if you have something like chlorine's right here, it wants to become like argon, so it's going to gain an electron. And if you gain an electron, we show it as a -1. Right next to our sulfur, it's going to gain 2 electrons, so it's going to be a -2. And that would be true for any in their family. So all of the halogens, fluorine, chlorine, bromine, iodine, they're always -1. Oxygen, sulfur, that family's -2. This family's -3. Over here, they're going to gain electrons. So lithium, I'm sorry, they're going to lose electrons. Lithium is going to drop back an electron to become like helium. So it has 1 extra. And right, so lithium would lose. So we show it as a plus. The 2A's are always +2. And then the ones in the middle are all the ones that are variable. And it's not just the middle here, it's the middle all the way to the line. So antimony, sorry, tin and lead, they have different charges that they can have. The thing, sorry, the variable ones are positive, it's just different positive charges. Another quick comment about hydrogen. Hydrogen has been made into a negative ion because it is a non-metal. That is a man-made one, and I think it shows up on the lab one time. I never ask about it again. There's very select niche uses for it because it's going to be highly reactive because in nature it never goes to a -1. All right. Aluminum is going to be a +3, and boron is an exception to the rule. It's in a really special place also in the periodic table. So we probably won't see boron for the next week. All right, that was just real quick. Hopefully you have your notes from that. This is the piece that you have to really feel comfortable with. And so with that, I am going to have extra office hours tomorrow and Saturday and Sunday because nomenclature, you can do it. You just have to take time to sit down and do it. And so if you need to go back and rewatch the video, again, I don't think I'm like God's gift to teaching it, but just having done it last term in this environment and for many years in a live environment, I know you can get it. And so this was in the video. I'm just going to walk through them, so kind of just listen. That when I ask for the cation, I want you to write the charge. So with magnesium, sorry, I lost my periodic table. That magnesium's here, that the earth metals are always going to be a +2. And so having a periodic table where you have that on there, and it just becomes ingrained for the students who had chemistry last term or before, they're probably comfortable with that. I am going to warn you, for those of you who've had this if you're still listening, don't get too cocky with it. Like, always look at your periodic table, because it's really easy to remember things wrong. So if you look, you can see, okay, magnesium, this whole family is always +2. And that is to get back to be like a noble gas. This is stability. This is nirvana. They want to drop 2 electrons back. They don't change their proton, so it's still shown as magnesium, but the +2 or 2+ is saying that lost 2 electrons. That is how magnesium is found in nature, always as an ion, because that is when it's stable. We see the ending "ide", so that is chlorine, and it's going to gain an electron to become like argon, so it's a -1. And then we just put them together. So that's the good news, because you guys tend to have really strong math skills in this class. You've had to make it this far. And so it's just a ratio of positive to negative that they have to balance. You have to have the same number of positive as negative. So for magnesium to give up 2 electrons, you must have 2 chlorines to give it up to. Sodium. So this is why for the first 2 weeks I kept mentioning, I mean, if we were live, you would have been required that you had to know your names. If you're hunting for names and you're not familiar with them, this is going to become more challenging. But sodium is Na, and it's right there. This first family is always a +1. The side is positive, the side is negative. And then nitride is nitrogen, and it's a -3. So if you come to ask for help, which I recommend you all come to make sure you're doing it right, or that you stayed today or whatever, is don't come in and say, I don't understand anything. Because I would just tell you, well, go back and watch the video. Tell me, okay, I understand that sodium has a plus charge, or I understand this part, and then tell me where you're getting stuck. So at least tell me what you can do. So please ask a very specific question. If it helps you to put the 1, you can. Most people don't show it, but on this case, we need 3 sodiums to 1 nitrogen. All right. And then calcium, it is in magnesium's family. If you prefer to write it as 2+, that's how most people do it in chemistry. I personally don't care if you show as a +2 or a 2+. Some people do, and that's awesome. Phosphorus is in nitrogen's family. So again, you can say -3 or 3-. So when they have the IDE ending, we're just dealing with the element from the periodic table, and we swap charges. So I talked about this in the video. When you have 2s and 3s, they always swap. So you can do, most students end up just doing where the 2-3 swaps. The reason that works, again, is calcium, you're going to the lowest common number, which is a +6 and a -6. You have to lose the same number of electrons that are being gained. So the ratio is 3 calciums to 2 phosphoruses. So what we're doing is we're saying this is the formula. If we have calcium phosphide, it's always 3 calciums to 2 phosphoruses. These are always empirical formulas, which we did the math for. Empirical formula means the lowest whole number. And because you can't have half of a phosphorus. And so we're doing the lowest whole number ratio. All right, and then potassium, hopefully you know potassium is special K, bromide is negative. So I often will ask this, and on the lab I do on the first 2 pages that I have you show your cations and anions. When you show your cations and anions, you must show the charge with them. And when you give the formula, you're just showing the ratio. There's no longer any charges there. We never show subscripts of 1. We always show the cation before the anion. That's how the nomenclature works. The other thing that I mentioned to make it nice is we're going to only be working with binary naming, And so binary means there's just always two parts, meaning one cation and one anion. In nature, so with rocks, that's actually more complex. So you'll have calcium and titanium and oxygen. So you'll have multiple cations and sometimes multiple anions too. The transition elements, we haven't talked about d orbitals. We do the quantum stuff again at the end of the term because we go in more detail, is that you would never, you're going to always have a Roman numeral. And that is always the positive charge. So that is for, these are ways to say who doesn't. The 1As and the 2As, because the 1As are +1, the 2As are +2, and aluminum is +3. These are fixed, meaning you do not use Roman numerals. All the other metals. So I cringe saying that because there's so much wonderful information online. And so when I learned this way back, whatever, 30, 40 years ago, there were like 20, I don't know, probably about 10 of these in here that were fixed, and you just learned them as fixed. When I started teaching, there were like 6 of them that were still considered fixed. There is still some people who teach that zinc and cadmium have a fixed charge. It turns out that's not true, and silver. So they show it as gallium, zinc, cadmium, that you don't use Roman numerals with those guys. I do, because that's actually the accepted nomenclature, because they have other possibilities. That's some of why the B group numbers are funky. So with that, let's just walk through these, and then we'll do some more practice. Or yeah, I want to talk about the polyatomics. So this 2 is actually your friend because it's telling you the titanium is a +2. So titanium's a +2. Chloride means Cl is just a negative. And again, this was all in the video, so I'm just going through all of that. If there is no Roman numeral, you're going with the periodic table. So barium is going to be a 2. You sometimes will see that. Actually, I'm going to go off on this, but so you would look up barium, you would look up sulfur. So since barium's in this column and sulfur's there, it's just these in the middle, I will have to give it to you. And so you put it together. When we go in the other direction, you always figure out the charge, the anion from the periodic table. Sulfur's still a -2 because it's in oxygen's family, and oxygen's family is always a -2. Because of this ratio of 2 to 3, the vanadium's a +3. It takes practice. You have to do, it's same like the empirical formula, it's same like the factor label. You have to practice it, and with practice, it's a whole language. If you learn another language, the only way you learn it is by immersion and practicing. But since the vanadium, since it's not in the first 2 columns, when we write the name of it, we have to say what the charge is. And we have to figure that out. Either the ratio is given where you can figure it out, or the charge was given to you. So I wanted to mention one more. I don't know if I did. If you ran into something like this zinc chloride, I avoid ones like this, but it might happen on the lab. And there are the first like 6 or 8 pages of the lab walks through examples. And so do look through those, especially if you've never done nomenclature, because you can do this. And I have found the students who spend the time, they get it, and then you're ready to move on, because in 2 weeks, we start putting this into chemical equations. So you want to feel comfortable. So if it doesn't give this number, this is where that table on this side, zinc is on the 2B. And so that's because that's what its charge is. So this old way of numbering gave us the number if the Roman numeral was missing. Again, that is just for gallium, zinc, cadmium. Those are like the only 4 that are remaining in some people's minds. And so I have to share the lab with other teachers. And so some of them still teach that those have a fixed charge. And so that's why you might run into it. So you can add the 2 there. You can always come and ask, hey, is that supposed to be a 2? And then you could get it from there. I usually do add the 2 now, but in case you run into that, I'm going to keep talking in case somebody's there, somebody can ask a question. So that was the first video. And so that you should feel, the idea is that you should feel comfortable with that and saying, yeah, I can put these simple ones together. I've got that. I can predict, I see where the charges of the ions. And so that's the first page of the lab. There's a second video, and I usually just talk from my brain. And so I want to go through a couple things that I know I must have talked about in the video, because we have ionic compounds, we have molecular compounds. So molecules, does anybody want to tell me what the word molecules means? Anybody there? Does anybody care? All right. I love teaching on Zoom. I just pretend like there's people there. So molecules means that it's 2 or more nonmetals. We're going to be dealing with binary for naming. So we're just going to see 2 nonmetals. And they are linked then with a covalent bond. That's actually, this is one of the big take-home messages from that video. And so it means that they're sharing electrons. Raven, did you have a question? No. Okay. Ions are going to be a metal and a non-metal. So they're going to be from the 2 different sides of the periodic table. And so recognizing that, that's actually really important, because when we get to what we're going to be doing and what the last 2 pages of the lab, it gets mixed up there. And so you want to be able to look at it and say, okay, this is a metal and non-metal. This is ionic, because they have 2 different ways of naming. Acids, how do we know we have an, oh, and so ions are going to be losing and gaining electrons. So you have the positive, negative. And so I talked about this. I know that sharing electrons is a true bond. It's unfortunate that we call these ionic bonds, and then there's hydrogen bonds, and we use this word bond. What's happening here is this is actually not a bond. It is just, big fancy word, an electrostatic attraction. And because it's just an attraction, it comes apart really easily. And then that's where you get ions. So the word ions comes from Io. So if you know any of your Greek mythology, Io is like all of us. She's immortal. And so she's roaming around endlessly. And so ions were named by Sir Humphrey Davy because they just meandered aimlessly around his solution when he was doing electrolysis. So several of you, I don't know if anybody noticed, when you talked about your elements, Sir Humphrey Davy showed up more than once. And he just happened to be in the right place at the right time, which was when electricity had been discovered. And so he was able to make a lot of elements from their ions, because he was able to force the electrons to move against nature. These are truly a true bond. They're sharing. So I'm pretty sure in the video I talk about, it's like your arm is attached to your shoulder. And so you need a chemical reaction to break a covalent bond. Ions, you just put them in water, so it's like holding hands, and you can pull them apart. So how do you recognize an acid? They get a special category.
Isn't there like a hydrogen in front of it?
There is. So you're always going to see a hydrogen plus. Do you remember what, Christian? What other type of element? Like metal or non-metal?
Non-metal.
Non-metal. Thank you, Spencer. Hydrogen plus a metal, we never talked about it in Chem 151. That's a man-made substance. The metal always is positive. Hydrogen can be forced into the negative. That doesn't happen naturally. But so hydrogen plus non-metal, and this gets a special category because hydrogen will take the positive, which means it's only a proton because it has no neutrons. Positive means it loses its electron, and it's just because of where it is. And that makes it why it burns us, why it etches glass, why it's been extremely useful for millennia. It was on the original periodic tables that would have earth, wind, and fire. They would have acid as an element because it was so useful. We now know it's not one of what we call the elements, that it's made up of multiple what we call elements. We think of it as hydrogen as a positive. It is not. It is a covalent bond because it is non-metals. It's a special type of covalent bond that we actually don't learn about until 222. Yeah, and so the water pulls it apart, which is different from ions, which are truly an attraction, and then they just become attracted to the water molecule. Here in an acid, the water pulls it apart. So that's like a fine tuning of stuff. It doesn't really affect our naming. But if you think of the hydrogen as a positive, the acids become named similar to ions, even though they're actually a covalent bond. So they are actually a special category of molecules. So for naming, we'll see. I know the ones from 151 will know this. I'll see somebody else. What is special about naming of the ones that are molecules that's different from our other two categories? This year from 151, might have to just count to like carbon, and then, or you can try and answer.
No, I was gonna say that I noticed something wrong. I was gonna say that it's only working with the non-metals, but I just realized that acids are also.
I already said that. I want to know when we name them, what's special? What do we use special when we name molecules?
Molecules get like carbon dioxide or tetroxide.
Prefixes.
Yeah, so I call them the counting prefixes. There's, I'm sure, a name for them, but you tell me how many are in there. So you all know that CO2 is carbon dioxide. And several of these people who are given the answers, actually everybody who has took a chemistry class with me before, and they will tell you it is. Initially, it's like, whoa, what's she doing? But just like the factor label, 2 weeks ago, I mean, some of you, it's still going, whoa, but you all are getting the hang of it. And it's very systematic. It's easier in the English language. For anybody who English is not your first language, the English language is crazy. Molecules, because they're sharing electrons, they are an absolute particle. It is always a carbon with 2 oxygens. These, it's a ratio. So no prefixes. So you do not, so for like MgCl2, you do not say magnesium dichloride. That is absolutely wrong. You will see things that are named wrong. A lot of things are named wrong. But we are going with the IUPAC rules, and so no prefixes. Here we do use prefixes. You don't use mono. I've only ever seen mono used with oxygen, so carbon monoxide. So I avoid mono, but they really don't put it with anything else. All right. So molecules are pretty easy. On the lab, there's one section of it either says molecular or covalent compounds. And so that's when you're going to use it. The last 2 pages, again, it mixes it up. And we're going to do that. We're going to go through practice here. The key to know you're going to use a counting prefix, it's kind of what Major was commenting, is you see only nonmetals. There's not many of them. Somebody made a comment, more than one. If you look at the periodic table, it's almost all metals. In fact, as they're finding all the new ones, this line keeps going over. There's very few that are nonmetals. But they share electrons to get to their octet rule. All right. The thing with the ions is, again, we had fixed, which is like the 1A's and the 2A's, so +1, +2, and then we have the variable, which get the Roman numeral. So that's what the whole first video was about, and that hopefully you might have to go back and watch that video if you're brand new. Watch the 2 videos. We're going to walk through though examples with these. Is besides just having the fixed and the variable, you can have the monoatomic and the polyatomic. And this is where you guys have a huge advantage, like outrageously huge, because you get to have your notes when you do your celebration. Your celebration does have a limited time, so you have to have an idea of how to use this, but there is a list on your lab of all the polyatomics. For those of you who are with me in 151, we go beyond the big 5, but I didn't put the list there. Sorry, I'm trying to find if I have periodic table. Yeah, so there is a list bigger than this, but there are polyatomics, which are when 2 atoms come together, like NO3, so 2 nonmetals, nitrogen and oxygen, come together and they didn't combine perfectly. And so the negative is they still need 1 more electron to have the perfect octet. And so we're going to see them, they're going to end with 8. Some students will say, or there's like these things, I think on Khan Academy, it's they ate an oxygen. So whenever we see the 8, it means with oxygen. The thing you have to be careful with, and again, you guys have an advantage, is you just want to always look at your chart because the number of oxygens is different. The chart is much bigger than these. These, though, I call them the big 5 because they are by far the most common. But there is a chart in your lab. You just want, like with the metric chart, you guys don't have to technically memorize the metric system. You want that chart from the lab, like in a nice place that you have it easy to refer to. I want to do a couple examples with these. Yeah, but they have the number of oxygens. There's a reason behind it. They also have the charge. And some of them, the charge makes sense because it goes with their family charge. One of the things that does happen, and this is more for those of you who've done this before, we expand into, say, like this guy, CrO4 2 negative, that the polyatomics can also be a transition element with oxygen. And so this is chromate. And again, the chart is there where they're all there. And so it's more just knowing how to combine them. So I guess we'll have to do it with chlorate. We'll do a couple with chlorate. So the polyatomics are, it can help to put a parentheses around it. The ClO3 is a package of a chlorine and 3 oxygens. I mentioned I write the L as a cursive L because otherwise students think it's carbon iodine and oxygen. That whole package has a -1, and that's known as chlorate. So we can combine it with any kind of metal. So we can do, let's say, titanium 2 chlorate. So if you see the name, you're going to be asked, okay, write the ions. And I usually see the 221 students. It's very systematic. The lab gets harder as it goes through each page, but it actually becomes easier because as you go through each page, you get practice, you get confidence. Yeah, it might be going back and watching like that first video again is just how to predict the charges and put the simple ions together. So you're going to first write your ions with charges. And if it helps you to put a parentheses, and then you put them together. So we'd have a TI, a couple things. If it is 2 letters in the symbol, the second letter is always lowercase. When you write the words, it doesn't matter. If it is just one symbol like the O, make sure the O is the same size as the C and the T. And the 3 inside tells us there's 3 oxygens. The 2 outside means there's 2 chlorates to balance the charge on the titanium. Now with that, we can then go, just do this. We'll do an easy one. So sodium bromide. So you start getting it and then you run into something like this. And you're like, hey, that's not on her chart. She told me everything was right there. I just needed the chart. You can go, actually, my son, his teacher just gave him a huge chart. And you can go and find these huge charts that have everything. To me, they're overwhelming because there's so many. And I actually like patterns. Patterns are good for your brain cells. You get more connections. That families behave the same. And so chlorine, bromine, iodine, mentally put them in the same family because they behave the same. And so if you know chlorate, sorry, I need my other one, you actually know bromate and iodate. So that's what we kind of wrote them all together. And then the ite means that you lost 1 oxygen from where you started. So sodium is Na+1, and then bromite must be bromine with oxygens, but 1 less than we normally would have started, and then we would put them together. When you put them together, I'm laughing because it's something that happened to my son. If there is only one of the polyatomic, you're not supposed to show parentheses. And so my son has me as a tutor, and I just know how he thinks and how a lot of my students think. And it made more sense to him. So this is the answer. You don't show parentheses. It made more sense to him to put the BrO2 in a parentheses because in his brain, he could see it, that's bromite and that's sodium. And he got marked wrong. He got marked wrong all throughout his lab, and he was devastated. I personally don't care if you put it in parentheses. I do care that the 2 is there, but I do find about half of you can get rid of those parentheses, and about half of you, the parentheses is how you visualize that this stays how it is. And so that piece doesn't matter. They're really not that bad. It just takes practice. And again, you guys don't have to memorize anything. So, but there is a chart. This is like the simplistic thing in the chart that you can add oxygens, and we put a purr for like the cat purrs. It stands for hyper. So it's 1 more oxygen than where you started. So technically, per phosphate would be PO5. The good news is the charge never changes, and that has more to do with Lewis structures and how electrons rearrange. If you take away an oxygen, the ending just changes to ite. So ite just means losing an oxygen. So nitrates and nitrites are really common because it's a food preservative that ends up making nitrosamine in your body and causes cancer and destroys your liver and is a class 1 carcinogen and all that good stuff. It's really hard to be a class 1 carcinogen, by the way. Plutonium is a class 1 carcinogen, and bacon is a class 1 carcinogen. But we don't have plutonium in the store, but people still eat bacon. I haven't figured it out yet. And then people wonder why they get sick. But you can't get anywhere near Hanford where the plutonium is. I've tried. If you take away 2 oxygens, so like from PO4, you would go down to PO2. It means you took away 1, and then you put a hypo, meaning below. So it's a systematic thing. Again, this little chart is in the lab nicely laid out, but it can be helpful to make your own chart. And by writing it, it's how our brain thinks rather than always looking at it. I would definitely have a printout or write it out in a really nice way. The lab, those 4 pages, you're probably going to want to do it more than once because it gives you really good practice. And then the acids are really simple, that anything that used to end with an 8 becomes ick, and 8 becomes us. We're going to do practice on the back side, so we'll kind of see how some of it goes. Yeah, and I have full confidence that you guys can do this. You just have to spend the time. So I have a couple notes to myself on here. We're going to do this back page. And so one is much gratitude and appreciation. You guys all did amazing. About half of you, I've read your papers and I put a grade on there. There were a couple people, and I put a note, you forgot to give me your references. And so like 1 or 2 people realized that, and they sent me an email with their references. So if I wrote a note and said I took off points because you didn't put your references, you can email me your references and then I'll add the points back. Same with the peer evaluations. There were a couple of you who forgot to evaluate yourself because we got done and a lot of people were tired and they just left. And so you lost, I forget, a point or 2. And so if you want, you can go back and evaluate yourself and send me an email and just say, hey, you took a point off. Can I get my point back? The other thing I want to mention, these were notes to myself. I always make it so you can submit more than once. So if you guys do have until next Thursday to get everything in. So more like if you turned in a worksheet, like say worksheet 2, and you only got 2 points on it, and you want to work on it on Sunday. Sunday's going to be this awesome rainy day, maybe even snow in there. And so that would be a great day to go back, get everything done. But it does allow you, or if you submit and you forgot a page, you can go back and submit it again. The nice thing there is this lab, you can submit it, and if I grade it and you're not happy with your grade, you can actually, I will mark which ones are wrong. I'll just put a mark on it and you can go back and try again. If you get it in by the due date, I'm going to switch the due date on your lab, and it's because Sunday's going to be a rainy day, and so I'm willing to do office hours on Sunday, and so I am going to move it so it's due Sunday at midnight. It's partly because Saturday is going to be a beautiful day. I will have office hours as always on Saturday morning from 10 a.m. I can stay as late as noon. I mean, if nobody's there at 11:15, I leave and go out. It's going to be a beautiful sunny day before the rain comes again. So I'll put a question mark there that I am anticipating. Like Major already changed his work schedule, so he could be there. But to have worked on your lab or to come to the office hours and work on it, one of the things that's a really nice feature is to take a picture of your lab, and so you can share the picture or you can email it to me, or you can even submit it and have me make marks on the ones you want to go back and look at. But you guys all know how to share your screen now. I can do a Sunday office hour if there is somebody who's interested. you can speak up now and we can negotiate, or you can just see and wait. And my other class, I offered to do one tomorrow for them at 10 a.m. So 10 until 11. Tomorrow's going to be a nice day too. And I get to take a nap on Friday afternoon. But if you are interested, just send me an email and I'll send you the link for the Friday one. The Saturday, Sunday one, they're going to be the same link. You just have to tell me if anybody's interested in Sunday. If nobody wants to do it, then I don't have to. But you can always email me. Nobody's talking now. All right. The other thing, before I forget, is I offered this last year. And I'm pretty sure I talked about what an affirmation is in my video, but an affirmation is when you say something positive. Cation is because they're positive. Why you're gonna see me dressed as a cat. So you can dress as a cat also. Or you can dress for the midterm for the celebration as a cat or a mole and you get bonus point for that. But this was actually really fun last year. And I was actually amazed, like the class was similar size. I think there were 24, like 4 or 6 people did this, that for 1 week, you just Google YouTube, not cat eye and affirmations, but positive affirmations or just affirmations. And there's all these like 10-minute or even 30-minute where you just listen to them and they do affirmations. There's some really weird ones out there. I mean, I thought they were weird. Most of you would find some of the ones I listen to probably weird. But if you want to do it, it's a type of meditation where you're listening to positive comments yourself, like for a week, and then you write up a page about this is one I listened to and this is how it went. So you basically listen to an affirmation soundtrack for a week. It should be at least 10 minutes. There's morning ones, there's evening ones. Some people do it laying down. You don't have to sit in the Om position with your fingers like in this fancy thing. You can do it while you're walking and go for a meditative cation affirmative walk. But anyway, you'd write it up and submit it next week. Yeah. And then I'll add bonus points to your, and you can dress up also to your celebration. There was another one. Now I can't remember what it was. All right. All right. We're
Sorry,
gonna do.
Are you
Go
going?
ahead.
Are you going to talk about the celebration at the end? About like how
Tuesday. That's all we're doing Tuesday. Well, Tuesday you have a study set due, but it's naming.
okay.
And then we're doing a review. So the notes for Tuesday is like a practice test that we'll do during this time. I'm finishing writing it, so it will be up there by Saturday. And then I'll talk about more details about next Thursday, but it will be during this time on Thursday from 6 to 8.
Okay.
Is that?
Yeah.
That's enough. And
yeah.
it's everything up through next Thursday. So yeah, I'll talk about more Tuesday. So right now, let's just get through this weekend and get through naming. Do the best you can. Again, you have till Sunday. I recommend trying it, get it in, and then some of you might find as you're trying it, like, hey, yeah, I want to take you up on those Sunday office hours. You just have to decide when. So, all right, as you go through these, so if I give you the name, of course, you're writing the formula. So the first one, what's special about that, we see the tetra. So there are no ions here, because this is covalent. So the ions are only for the ones that are metal and non-metal. So this is blank. If you can't handle blank, draw a Valentine, draw a unicorn, draw a beautiful picture or something, or just cross it out, like put a big black box there. So this is just telling you, you have silicon. That I has to have a dot on it. And then you have the tetra is that you have 4 chlorines. This is different from this one here, where this 4 is referring to the lead and saying the lead has a 4 charge. So the Roman numeral is not how many you have. The Roman numeral is the charge of the metal. So lead is Pb, and if you don't know your elements, you're going to learn them. And nobody did plumbum as their element. All right, I already told you how much I had a great time doing. Right, and then sulfide. So IDE means it is just sulfur. One of the biggest mistakes that's made is students want everything to be polyatomics, because as soon as they get to the polyatomics, or they start going and start hyperventilating. That's why the affirmation meditations are really good, because they help you to breathe slower. All right, sulfur is a -2, plus you get some bonus points. I'm laughing because I got to read some people's comments last year, the people who did it, and they were really funny. So I have this one on here, and I know I skipped that one. The ratio. So some students get in this habit where they say, okay, you just switch them, which you can do, always the switcheroo. But if you do it here, you're going to get the wrong answer. So they say, okay, I will need 2 PBs and 4 sulfurs. So you can do that, but then you have to take a deep breath. This is a very meditative process. Approach it as a meditation. Approach it with love. Doodle cats meditating all over your thing if you like. Meditate with your cat. Cats are really good meditators. This has to be the lowest ratio, empirical formula. Ionic is empirical formula. Covalent is whatever I give you, you write it. So we have to reduce it to a 1:2. So it should just be PbS2. You only need 2 sulfurs. Sorry, I'm looking.
No, I just want to
Say
comment.
again.
I did what you just said that some people might do that. I just switched them over and I ended up not going to the lower. So
Yeah, so it's if they're both even, you have to be careful with it. So just be careful with that. All right, the one above it, potassium's K and Ide is just F negative. So I like to underline. I like to use colors. Again, somebody actually, one of my students, my class last term, they were all getting these on Amazon because they're erasable colored pens, and they actually come rainbowed in that order. I didn't have to be geeky and do that, but
I actually bought like an 18-pack of them, and I love them.
Oh, really? Yeah, it was
Yeah.
actually really interesting because that's Maddie. Last term, it wasn't your class, but I noticed in all 3 of my classes that as the term went on, people started using more and more color. And so I didn't know there was an 18-pack. That's fascinating. That would be too much for me probably. But now I have orange. And so this is just KF. We don't show the ones. All right. If you're given the formula, we just break it down into the ions, so sodium and oxygen. So your teacher can do that without looking at the periodic table. I don't recommend that you do. I recommend that you just take a deep breath. Now, some of you, as you've become more and more familiar, have your periodic table there. And yeah, sodium is a +1. Oxygen, you're going to know oxygen. And so I want to see the ions in the center, no subscripts. We show the charges. In the final answers in the columns on the outside, yeah, this is the ratio. And here it is just sodium and oxide. So oxide means it's just sodium with oxygen. All right, Ti and Cl. So Cl we know is a -1. And Ti is in the middle. So its charge, we figure out there's 4 chlorines. So the titanium's a +4. Now, because titanium's in the middle, when we write the name, we want to put a Roman numeral with it. So parentheses and then chloride. IDE. That I separated this really nicely. I wasn't as nice on the lab. So the polyatomics show up next. So this number here is this charge, the 4. I do need to be able to read your handwriting, and mostly I can. The biggest thing is the ending, IDE, because there's also ITE, so you need to make sure that's very clear what it is. All right, now this was kind of comment what Major said before. This is a mistake that students make. They go, oh, I see the 2 there, and they say, oh, my tin must be tin 2. And then the sulfur, that doesn't work because sulfur is right there as a -2. This number is not what the tin is. The tin has to balance out the 2 sulfurs. There's 2 sulfurs. Both sulfurs are -2, so the tin is actually a 4. So it's what happened up here, but backwards. This page is actually good practice to go back and print and do again. So in the name, it is tin 4 sulfide. Ti is titanium, SN, tin is a sin. It's actually such a wonderful little thing. So again, the middle, which is here, but it's all the way over until we hit that staircase of the metalloids. So tin and lead always get a Roman numeral. Indium and thallium will also, actually bismuth and antimony do. Antimony is an interesting one because antimony can show up, the metalloids can show up as ionic compounds and as molecular. That's because they're in that special place. And so, yeah. All right. So magnesium is Mg.
Hi, I have a question about
Yep.
number 5 with the titanium.
Yep.
Can you go in more detail how you get the 4?
Chlorine is -1. That I got from the periodic table. You're okay with that, Lisa?
Yes.
And since there's 4 chlorines, so 4 times -1 would mean I have a -4. So my titanium must be a +4.
Okay, thanks.
It's a ratio thing, and I do find that it just takes practice, and you just start seeing. And there's only certain numbers that show up. So like the negatives really are going to be -1, -2, -3. You're not going to get other negatives than that. The positives, 2 is like 80% of the time it's +2. There's only a few that can do a +1. You do run into +3s. You can run into 4s. There can actually be 5, 6, 7, 8 now, but they're very rare. And so really you pretty much are dealing with just numbers from 1 through 4. So there's only certain ratios that are going to exist. Thank you for that question. So be careful with the ending. So again, now we're going to do the polyatomic. So the 8 means you're going to look at your little list. I just have mine here. So phosphate, and you just write it exactly how it is on that list. So it's PO. You want to make sure, kind of now thinking about Lisa, because you want to make sure that oxygen is the same size as the P, because this is not polonium, this is phosphate. So it's a P with 4 oxygens. That is a package altogether. And then this is a -3 charge, or 3 negative. Again, I always write it as -3. But again, it is technically 3 negative. So back to what you had said, Major, whenever you see the 2 and the 3, that always swaps. You can do that for all of them, but then just be careful. But they will always switch places, meaning you're going to need 3 magnesiums for every 2 phosphates. 2s and 3s always swap that way. And that has to do with the lowest number is 6. So 2 times 3 is 6, and 3 times 2 is 6. So 3 magnesiums. PO4 is in the parentheses, and 2. Another really common mistake, and I kind of giggle because everyone does this initially. You start getting into the pattern, and this number here, this subscript, it becomes like a helium balloon and it just starts floating up to the top. When you write the formulas, it is subscripts. So do this as a meditation. Take a deep breath, do it very slowly. You can listen to your cation affirmations as you're doing it, and then write up how your day went. I'm laughing because there was one student who I'm actually still, I keep in contact with him, very fond of him. And he said they were making him really angry, that the affirmations were like bringing out this inner anger. And he was like the gentlest, quietest student. And so I was like, whoa, what's happening here? All right, so this 3 goes with the iron. Iron is Fe, so ferrous, and it's a +3. And sulfate is SO4 with a -2. And again, I got that from the list. So I just made my own little list for today. Yeah, because I didn't deviate. You can write it like this without the parentheses. If you want to use the parentheses, you can. So again, we have the 2, 3 things. So they're just going to switch. So 2 irons. So they switch. This becomes a subscript. And then the SO4, we do have to use a parentheses. If there is more than one of the polyatomic, you must use a parentheses. Just real quick, because I'm thinking of it, because there's 3 questions on the lab that are the most missed questions. And so this is especially for those of you from 151. There are 2 new polyatomics. One is chromate, and then there's actually one that is it's in the list, CR2O7 -2. Sorry, my headphones, like certain things are really loud today. I think it's because it's Thursday and I'm sleep deprived. That should be a -2. So it's CR2O-, and it's called dichromate. And it's really unfortunate whoever named it as dichromate, because students think it means you have 2 chromates, but it doesn't. It was just something that was not named correctly. And so just be careful of that. It's a CR2O7. It's there in the list, and it's actually really common. All right, the next one, when we see the ite, it means we go to our list of chlorates and we just take an oxygen away. Now you can make your L, it's a little L, it has to be a little L. You can make it as a line. That confuses a lot of people because they think it's iodine. So that's why I always write it as a cursive, and it's a -1. So if the parentheses help you, absolutely, please use the parentheses. I just want that you get the idea of how to do this. Because again, we keep building on it, and it allows us to communicate in the class, because we're going to get into chemical equations. So chromium 3. And yeah, and again, the lab walks through a bunch of examples, several of those pages. You don't have to print the whole lab, but it can be helpful. You're only submitting those 4 pages that have you fill out. So they do switch. So for every 1 chromium, we need 3 chlorates. So ClO3, well, I'm sorry, it's chlorite, so it's ClO2. So ClO2 inside. So ite again means it lost 1 oxygen. And then 3 on the outside. So the outside 3 balances that charge 3. And the 2 on the inside is from the ite. So the ite is why we have the 2 there. All right. Mn is manganese. And yeah, so Kyle did that element. That was pretty cool. I really enjoyed your guys' presentations because I've never done them early in the term. And you guys did such unique presentations because I think because where we're at in the chemistry, you didn't get bogged down with all the chemistry. So there were some really cool and reasons why you picked different elements was also extremely cool. We're going to have to figure out the charge of the manganese. So Mn. Now to figure out this charge, it's here in the middle. It's not going to be 7. We have to figure out what it is. It actually can be 7, but it's not here. And then the NO3. The NO3 is that polyatomic. Now, when I give you the formula, you want to always with the polyatomics. I had some students one year. This is why I did this with my periodic table, and they asked me to do it. And this is the periodic table with a whole bunch of writing on it that you actually would get in class, because it basically had what we needed. And they said they actually liked writing the polyatomics on the periodic table, so they weren't looking over here at a list and over here at this and over here at that. Everything was just right here in one place. So it can be helpful. But NO3, you want to look at the number of oxygens. So it has 3. In this, inside my parentheses, it has 3. So that is nitrate. It is the 8 ending. And it is a -1. So you can just write the negative. Now this is back to the question Lisa, you had just asked. So there are 2 nitrates. That's the 2 out here. Each one has a -1. So the Mn has to have a +2. So if this is a 2 and this is -1, that's where we're getting this 1-to-2 ratio. It's always a ratio. And then, now that we know it's a 2 charge, we say it's manganese 2 nitrate in the name. And again, it just takes practice. You will get this. Everybody does. Now, something that can help with this next one, everything is I was going to say bipolar. That's what I'm feeling like right now, but everything's binary. So there are only 2 pieces. So the lithium is our metal, and then the BrO4, that all stays together as my non-metal. So if you want, you can add a parentheses to say, okay, I have lithium and I have BrO4. So lithium is right here, so +1. And then the bromine with the oxygen, remember the family, so chlorate, bromate, and iodate, they all look the same. It normally is 3 oxygens. This is 4 oxygens. So lithium, no Roman numeral, because first 2 columns, no Roman numeral. Extra oxygen, so this one has an extra oxygen. And so this gets the per, and then bromate. And it does not need to be capitalized. I have no idea why I capitalized it. We do want to show the charge here. So that middle column where it asks to see the cation and anion, you do show the charge there, but we don't show it in the final formula, and no Roman numeral in the name here. So perbromate means the extra oxygen. So that's where the per comes from where it normally started. All right, the next one.
Sorry, I just
Yeah.
want to
Go ahead.
understood that right. So when you put the per first, you don't capitalize the actual letter of the actual element.
I don't really care.
Okay.
But yeah, it's none of these are capital letters. I don't know why I'm capitalizing. I think it's because it's Thursday and I'm extremely tired.
No, I was just making sure, but thank you.
If you capitalize, I don't care.
Okay.
The time I do care about capitals, and this is an excellent question, is when you write the formula. When you use symbols, you have to show the symbols correctly. When you write the names, you can, like my dad was an engineer, he wrote always in capitals. So if you're trained as an engineer and you write in capitals, the words can be written in capitals, but the symbols have to have upper and lower case correctly. Hopefully that makes sense.
Yep.
All right, again, 2 parts. So we have copper, and then this must go together, the SO3. Something I want to mention, again, especially for those of you who had 151, because we've run into a bunch of new polyatomics. There are, again, the transition metals, the chromium and the oxygen. In this case, there would be something in front of it like sodium. So the sodium is the one part, and then the chromate, the chromium stays with the oxygen. So just something, and that's why you're probably going to want to work on this and then find time to come in to an office hour. Right, the SO3, you look at your handy dandy table. So we find SO4. So this one lost an lost, but it's still the same charge. It's still a -2. So as they change the number of oxygens, the charge does not change to the polyatomic. And so that's why you can just have, right? That's why the list has those. So this is sulfite. I'm giggling because I wrote a capital again. And so the ite means it lost an oxygen. So again, it's a systematic thing. Copper gets a number. It always gets a Roman numeral. We have to figure out its Roman numeral from this ratio. A lot of people want to say, oh, it must be a 3 because it's that 2-3 switcheroo thing, and it's not. And so this is where those parentheses are really helpful. So putting a parentheses around the SO3, there are not 3 sulfites. There's only 1. This one sulfite has a -2 charge. So this copper, each one must have a +1. There's 2 coppers, each one has a 1 charge. That's where we get the 2 from. So it's copper 1. You do show Roman numeral 1s. They are not very common. Copper, silver, gold. In Mendeleev, if you look up Mendeleev's original periodic table, he actually put silver, copper, and gold in the same family as sodium, potassium, and lithium because they form the 1 charge. They didn't know why at the time, but it was based on chemical reactivity. All right, the next one's a funky one, and I put this one on there. NH4 is a polyatomic, and then the chlorine is just chloride. IDE because it's not a polyatomic. NH4 is special. In our class, it is going to be the only cation polyatomic we will see. There are other ones, but this is the only one we're going to see, and so you just want to be careful of that. It would always come first. It is not, AM is americium, which is not ammonium. Ammonium is NH4, and so that would be our cation. There, I made myself write a lowercase letter. It took effort. So ammonium chloride, they are 2 separate words. Remember, everything is binary. There's 2 parts. So you have to find the 2 parts, and adding those parentheses can be really helpful. All right, the next one. This is covalent or molecular. It is 2 nonmetals, selenium and 2 oxygens. So again, nothing there. Cross it out, it's a blank. And so selenium dioxide. This is where, when it's covalent, you just tell me what's there. You don't do anything with charges. Now, if you missed that it was covalent, let's say you pretended you were trying to do charges, well, you would get selenium as a -2, and then you would get oxygen as a -2. And so if you tried to give them both a negative charge, that should hopefully key in somewhere where you go, oh, this cannot be negative. They can't both be negative. They're both nonmetals. That you tell me how many there are. So 1 selenium. And the second element always changes the ending. The first one, we keep its name like manganese, tin, selenium. The second one is where we change the endings to ides, ites, and eights. All right, finally, an acid. Oh, the last 2. So acids. if the formula is given, the hydrogen is always given first. When you write the name, you say acid at the end. So it's a word of warning. Acids burn us. It's because of the hydrogen. Hydrogen is our ion. Now, if you prefer with acids to not show ions, that's fine also, because technically they're not. I'm going to show them here because it helps me to explain how the name is done. But again, technically you don't have the ion until the water pulls it apart. So these guys are always aqueous, which means they're dissolved in water. So yeah. And for those of you who are with me for the whole year, including summer, in 223, half of 223 is just dealing with acids and pH and stuff. All right. And so my other half is the CO3. So the hydrogen comes off, and then the CO3 is a -2. I get that because it's with 2 hydrogens, or from looking at my polyatomic list. Right, the key with acids is the 8 changes to ic. So this was carbonate, and so now we call it carbonic. So the acids, they often have 2 syllables before the ic. If it had an ite ending, it goes to OUS. There's like a page that talks about this with the acids, and it takes practice. So it's finding the time to practice. And again, I'm going to move the due date to Sunday. Probably won't happen until tomorrow, but and you can just let me know if somebody wants an office hour Sunday. Speak up now. I'm going to write these as ions again. Just on the lab, it doesn't have you. It has a little section of them, but it can help. On the last 2 pages of the lab, it's me just realizing I had meant to go and fix this, and then I never did. It doesn't have this middle column of showing your ions. It can be really helpful to write the ions because that helps you to figure out the charge or the ratio. But it doesn't require you to on those last 2 pages. So chloric meant that this was chlorate. And so we look it up on our handy dandy chart, which is ClO3 negative. So we think of it, we treat it as if it's ionic, but it's really going to be a covalent molecular compound. So it's an H, and then ClO3 is the compound. I want to add one more acid. And that is, I should have written this in a different color, hydrochloric acid, which I'm pretty sure you all heard of. And again, back to the comment from Major, I don't know why I was capitalizing. You don't have to capitalize, but when you write your formulas, if you have this prefix hydro, the hydro, so this was a comment that Maria, who talked about oxygen. So oxygen was named because they thought that all acids had oxygen in them. And so I forget who named it. They got that wrong. And so hydro means without oxygen. It meant there's hydrogen there. And so when they did the naming, they couldn't figure out why it didn't have oxygen. But it turns out the term acid actually means with hydrogen. So hydrochloric acid means there's no oxygen in this compound. It's just hydrogen and chlorine. Now with that, whenever we name something as an acid, again, it means it's dissolved in water. It means it's an aqueous. The ones that have no oxygen, they can be found as a pure substance. So aqueous means it's mixed with water, which are all acids. But the ones with no oxygen, they also have another name. And I mention this because I'm pretty sure it shows up in the lab. HCl can be found as a gas, meaning pure, not mixed with water. and then it is not named as an acid, then it is named as a covalent molecular compound because it hasn't been pulled. It can't be pulled apart because there's no water. The problem is you and me, we're 71% water. We're going to pull it apart and then we're going to go, ouch. We're going to do more than ouch. We're going to scream probably because we're going to have all these protons that are looking for a nice humble home. But when it is pure, you just name it as the two parts, hydrogen chloride. They leave the mono off. And so it would just be hydrogen chloride. In the lab, there's one section, I think this shows up in two places. If it shows up, sorry, my handwriting got cramped there. In the part where it is the covalent molecules, you would name it like this. You can add that it's a gas. Same like hydrogen fluoride. I don't know if anybody works in the semiconductors. Hydrogen fluoride is actually extremely dangerous because it's going to search out for calcium, and our body has a lot of calcium in the bones. And so very different from hydrofluoric acid where it's already in the water, but in the pure substance, it's extremely reactive, and using caution. If you see it in the section of the lab that you're working with naming acids, you would name it as the acid as hydrochloric acid. If it doesn't specify, you could do either name. Yeah. All right, questions? Or does anybody want to pick a time for Sunday, or I'll just go with whoever emails me? Or wait until Sunday when you guys suddenly realize you might need help. All right, so again, I do have an office hour tomorrow. I'll put the link on our Blackboard if you want to stop in. I will be there Saturday morning. And I am moving your lab to due date as Sunday. All right, I'm going to stop. Oh, that's not what I wanted.